So good afternoon to all of you. Dr. V Ramanathan has joined us now after the busy schedule. I welcome Dr. V Ramanathan for the invited lecture, and I must say thanks to him that within a short period of time, he accepted our invitation. So let me just give a brief introduction about Dr. V Ramanathan, although he does not require any introduction, a very prominent researcher in the field of laser spectroscopies and all computational chemistry. Just few lines for him. Dr. V Ramanathan has completed his PhD, if I'm not wrong, from IIT Kanpur in 2008, and after that he went for 3 postdoctoral fellowships in South Korea, Switzerland, and Germany. Followed by that, he joined Department of Chemistry, Shastra University in 2012, and in 2019 he joined IIT BHU as a permanent faculty as an assistant professor. So many awards he garnered from his research. The few prominent ones are the Indian National Young Academy of Sciences in 2016. His major research interest is to use the various spectroscopic tools, starting from laser spectroscopy, like maybe the transient photospectroscopic techniques, Raman spectroscopy and imaging, and various computational chemistry tools. To his credit, there are more than 35 publications as far as I saw, and 400 plus citations. So with a just small brief introduction, I would like to hand over the session to Dr. V Ramanathan and thanks for giving us the time as well. Dr. V Ramanathan, now please over to you.
Thank you, Dr. Nikhil, for this opportunity. I apologize that it was delayed from the slated scheduled time.
No problem.
Thanks for accommodating my last-minute request to postpone it from 11:30 to first 12 and then to 12 to 12:15.
No problem.
Sorry for that. So I believe I'll speak for around 40 to 45 minutes.
Sure.
And then if there are any questions, I'll be very happy if I'm able to answer them.
Sure.
Okay. So straight away, let me get into the topic. I have given my topic of today's presentation as revisiting the computational chemistry of Alkane Thiols, but half of my talk, at least 20 to 30% of my talk, I'll first give a brief I'll give an introduction to the subject, and then I'll get into the results about the Alkane Thiols that our group has recently worked upon. I hope my screen is visible to you in the full screen mode.
Yes, sir, it is visible.
Okay. So basically, look at what is science. Science is nothing but trying to understand or trying to get control of the nature with our limited capacities and instruments and means of probing the nature. So this always reminds me of the our traditional story from Panchatantra or Hitopadesha, where 5 blind men come and touch the elephant and describe the elephant based on their own experience of what they felt when they touched the elephant. So to me, science is also something similar, where each section of science, each specialities of science try to probe nature in its own limited ways and try to come out with the reality. So it is at the same time both true as well as false. So that is the way I look upon science. And added to that, in order to not philosophize things, the way we work with science is to have a holistic understanding in a universal language so as to exercise control. So exercising control is one of the chief goals of the modern science. And quantum chemistry really helps a lot in terms of understanding this, having a holistic understanding, and to also communicate in a universal language whereby you can exercise control. So in my presentation, so I'll be briefly introducing this subject because it's a workshop on computational chemistry. I thought it will be good to introduce, even though some speakers might have already introduced to you some of the basic concepts of quantum chemistry. I thought nevertheless it will be a good idea to revisit them and reinforce these concepts so that some conceptual clarity is there. And then I will talk about the results on alkane thiols. And I am also very fond of history. So history of science is also one of my pet peeves. So even for my regular class, I kind of introduce, before I introduce the scientific part of it, I dwell a little bit on the history. And the history of quantum chemistry is really, in that case, a very interesting and a very checkered history. It starts from 1865 when Maxwell had kind of married both electricity and magnetism. And that's where the electromagnetism came into picture with his very famous 4 set of equations, which are known as Maxwell's equation. And if you look at the remaining 35 years, it's very interesting period after Maxwell's integration of electricity and magnetism. So much so that even a person like Lord Kelvin had to say this: there is nothing new to be discovered in physics now. All that remains is more and more precise measurement. So you could see the impact of unifying electricity and magnetism by Maxwell, where people felt whatever had to be done has already been done and nothing need to be done further. But then we know, right from 1890 onwards, and 1888 in fact, where photoelectric effect was first discovered by Heinrich Hertz, followed by radioactivity, followed by Thompson's electric charge measurement, discovery of electron. So the period 1890 to 1920 is very good, very active and most dynamic period in the history of physics. And somebody has written a book by name 30 Years That Shook Physics. And this is a period where quantum chemistry also had its birth. We all are familiar with this failure of, or I would not say failure, I would say lack of theoretical backing for certain observations that were made during these 30 years, starting from the black body radiation. Okay, so the black one that you see here is the classical theory, and the red, green, and blue are the experimental observation. There you see, as the temperature rises, the lambda max shifts towards a higher energy. This, the then existing theory could not explain. This is, then comes the famous Max Planck in 1900, who gives a new formula to describe the black body radiation behavior, which could not be explained by the then Stephen Boltzmann or Wien's law. So this creates a big furor in the whole scientific community, because for the first time you are able to come up with an explanation for a black body radiation. By then there were several other observations also. So if you recollect, the Rydberg formula was a very empirical formula for describing the hydrogen atom spectrum. That could not be explained. But even Planck's constant could not explain. It had to wait for 10, 12 more years, where Niels Bohr comes and uses the Planck's constant and explains the atomic spectra. So now the Max Planck, with the Max Planck formula, black body radiation could be very easily explained. And that, as I said, was a real breakthrough, and comes because Planck has quantized the energy, and he said that now energy will also come in packets or quanta. The way I explain to students in my class of quantum chemistry is that you understand it from the point of view of economics. So today, when you check your bank account, you will see that when you kind of look at your bank account balance, you will have only 2 decimal places. But there is nothing, since all is digital currency, why should we restrict it to only 2 decimal places? Because today we have agreed upon the fact that 1 paise is our minimum denomination with which we do the transaction. That's an artificial construct, 1 paise, right? Similarly, nature has got the minimal denomination or transactional value, which is called the quanta, and that is precisely measured, or precisely values given by Max Planck as 6.6 into 10 to the power minus 36 joules second. So this is intrinsic. This is nothing, at least 1 paise is an artificial construct by human, whereas Planck's constant is intrinsic. Once again, this is not a limitation of experimental technology. No, no matter how sophisticated the experiment becomes, this intrinsic transactional value of energy will remain so. What we may do, we may end up measuring it more precisely, but this is a minimum denominational or minimum transactional value of energy. That is what is Planck's constant. Albert Einstein makes use of it, and whatever was unexplained for the past 15 odd years, Albert Einstein explains the photoelectric effect using Planck's constant, and lo and behold, he gets a Nobel Prize for explaining photoelectric effect. Many people believe that Einstein discovered photoelectric effect. That's not correct. Einstein never performed any experiment in his whole life. He was a theoretician. And he got the Nobel Prize in 1915 for explaining mathematically the theory of photoelectric effect, which was observed way back in 1888. Then 1911, Rutherford comes up with his experiment and discovers the atomic nucleus with the positive charge. And then you have Niels Bohr giving you the atomic structure. So these were some of the most important historical milestones in the development of quantum mechanics per se, or quantum chemistry. So this atomic structure we all very well know, and I don't want to spend more time on that. And some more years had to be waited until 1920s, where Otto Stern and Peter Gerlach performed their eponymous experiment and discovered the spin, the intrinsic spin that the electron possesses, or for that matter, even the protons possess, subatomic particles possess. It's a very famous experiment. They got the Nobel Prize for this also. It's a very, very famous experiment. Those of you interested should read the book of N. Sakurai. And Sakurai is a book which starts with the subject of quantum mechanics from Stern-Gerlach experiment. So I'll not get into the details, but the summary of this experiment is that Otto Stern and Peter Gerlach announced the existence of the spin component of electrons. Then what follows is some of the most important milestones, like de Broglie comes up with the de Broglie wavelength of electrons. So earlier the photon was considered both as particle and a wave. Then when Rutherford discovered nucleus, it was considered as particle, but then de Broglie showed through his experiment of interference, he showed that even matter behaves like wave. Then Schrödinger comes up with this very famous equation to describe the subatomic behavior. And then what followed, then Dirac comes up. Even the Schrödinger equation, the problem was that you could not explain the spin part. That was explained by Dirac by considering a relativistic effect. Then by 1930, things were ironed out. All the existing problems in quantum mechanics were agreed to have got solved, and people were quite happy. Then this is called early development of quantum mechanics. But then later you had the field theory, so that got revolutionized further. But I'll not get into those details for this presentation of mine. As far as quantum chemistry is concerned, and as far as the ground state of any molecule or atom is concerned, the results that were agreed upon by almost 100 years back are good enough for us to work in the chemistry field. A little bit of, that was the historical development, little bit of mathematical background for this. What all you need to know, basics are vector space, the dimension, linear independent vectors, what is subspace, basis sets, initial value problem, boundary value problem, eigenvalue problem. Types of differential equation, namely first order and second order differential equation, that too linear differential equation. We do not explicitly solve the nonlinear differential equation because nonlinear differential equation does not have an analytical solution. You have to have only approximate solution. And believe you me, whole of quantum mechanics is a nonlinear differential equation problem combined with linear algebra. So with this basics, you create a new language for quantum mechanics where you make use of operators, you make the operator operate on a function, and what results is an eigenvalue, and that eigenvalue is what something you measure. So suppose you have a position corresponding to that in the classical world, if it is a position, in the quantum world it is referred to as a position operator. Similarly, in the classical world, if there is a potential, you refer to it as a potential operator. in the quantum world. When it comes to momentum, you have the momentum operator defined in a slightly different way, where you have minus IH bar d by dx as a momentum operator in the quantum world, whereas in the classical world it is mass into velocity. We know velocity is differential with respect to time. Dx by dt becomes a velocity, but this is where conventionally the quantum world changes. So without getting into much detail, you can understand this as this works as the momentum operator takes up this mathematical form IH bar minus IH bar d by dx or d by dy, whatever the derivative, in whichever direction you wish to choose. Then corresponding to the energy in the classical world, you have Hamiltonian in the quantum world. And like energy, we have potential and kinetic energy. So the Hamiltonian part also has got the potential part and the kinetic part. The kinetic energy, we know from the formula, it is mv square by 2m, or half mv square by, it's like p square by 2m basically. P is your classical momentum, which is mv, so mv square by 2m. Same thing, you look at it, because momentum is defined as minus IH bar d by dx, you can write the kinetic energy operator if you know the kinetic energy formula as p square by 2m, and p in the classical world is mv, in the quantum world it is minus IH bar d by dx. You just substitute that and you get this expression for the kinetic energy in the quantum domain as minus h bar square by 2m d square by dx square. So it's a second order differential operator, kinetic energy, and to that you add the potential operator v of x, and that you get it as your energy operator. And as I said, in the quantum world, you use an operator, you make it operate on a function, you get something called eigenvalue, and that's something which you can measure it using experiment. In this case, when you use a Hamiltonian operator, the eigenvalue is the energy. When you use a momentum operator, the eigenvalue is your momentum. So that way you should understand it. So this is how the Schrodinger equation is built. I'll not get into the details, or I'll not get into how it will be solved. But why are we doing all these things? Because we need to study the system. If you remember my very first slide, I said we need to understand the nature. We need to understand a particular system. And in our case, chemistry, the system comprises of molecules which are built up of atoms. And each single atom is made up of electrons and nuclei. We need to study that. We need to study the dynamics of, or we need to study even the static model, how each of these subatomic particles interact with each other. What's the consequence of this interaction on the energy? So for that we need model systems. So we start with hydrogen atom, then we have rigid rotor, then we have harmonic oscillator, we have one-dimension box. So this is standard way to introduce quantum chemistry throughout the world, whether you are sitting in India or in USA, in MIT or Harvard. This is the basic thing that normally the whole structure gets, the whole subject gets introduced, right? So you have a 1D box model for which you solve the Schrodinger equation and you get the energy. Since this is not a class, I will not get into the solution part, but I'm just giving you a glimpse of how the solution looks for each of the model system. This is for the hydrogen atom, and hydrogen atom has got two parts: the spatial part, which is R of R, and the angular part, which is your y theta phi, which is called the spherical harmonic. And R of R will be solved differently. Y theta phi will be solved differently. So you have different solutions. The R of R, when you solve using Laguerre polynomials, you get the different orbitals. That is your principal quantum number. When you solve your y and theta phi, that's where you get your angular quantum number and your azimuthal quantum number. So if you recollect from your school days, electrons or every subatomic particles will have 4 different quantum numbers, or principal, or azimuthal, orbital or magnetic, and finally spin quantum number. The first 3 quantum numbers are nothing but your solution of your one electron system, which is a hydrogen atom problem, where R of R gives you the principal quantum number, which is your n is equal to 1, 2, 3, so on and so forth. That comes from the solution of this equation. Your L and M, or azimuthal and magnetic quantum numbers will come from solving this equation, that is y of theta phi. I have shown you two different equations here. This equation depends only on the r, this equation depends only on theta and phi. If you solve them, this solution will contain only r, which is a principal quantum number. This equation will contain both theta and phi, that's your azimuthal and magnetic quantum number. But you do not get the spin quantum number from solving Schrodinger equation. For that, you need to solve Dirac equation. But we will not need those details for the time being. So ultimately, the solution will look like this in the case of your hydrogen atom or one electron system. This is a y Lm theta phi. So you know the relationship between L and M, that's what is reflected here. And solution looks something like this. And the same thing when you plot it on a polar graph sheet. Normally the graph sheet that we are used to in the high school is a Cartesian graph sheet where you have x perpendicular to the y, two axes are perpendicular. You can imagine a similar polar graph sheet where you have r and theta. Of course, you will not have phi because phi you need a third dimension. In the polar graph sheet, you will have r and a theta. And if you plot the solution of the one electron system on a polar graph sheet, they will resemble they will come up with some shapes, which is what we call as our s orbital, our p orbital, and our d orbital. Yeah? So with this I will actually stop 15-20 minutes. I've given you the grounding, historical development as well as basics of quantum chemistry. Now when you come to helium atom, what happens is you have two electrons and then you have the interelectronic repulsion, which is going to make the equation unsolvable. So the equation becomes nonlinear and you need to resort to approximate methods. And thanks to the introduction of computers after the Second World War, solving such nonlinear differential equation became quite easier with the help of computers. So John Pople, who got the Nobel Prize for introducing computer to chemistry, credit goes to him for in fact making the job easier by taking help of computer to solve the Schrodinger equation. So this is one example where I've shown you when you have two multi-electron system, how the spherical part, how the R of R part. If you remember in the hydrogen atom problem, you had a R of R part and a theta phi separately, right? R of R and theta y of theta phi. So as the system changes, the R of R can also take multiple mathematical forms, and here is one such form which needs to be solved, and that's where Pople comes and he takes the help of Gaussian function. So here, if you carefully pay attention, this is like called a Slater type orbital, which is what is going to describe your system. See, this is called a cusp, but this is basically involving exponentially decaying functions. Of course, the second quadrant is of no use. What is meaningful is only the first quadrant part, where also if you see it is e power minus something, which is an exponentially decaying thing, and there is a cusp here. So that is quantitatively, this is replaced by involving three Gaussian functions. This was the genius of John Pople. Said, okay, I will not be able to solve this numerically, but I'll approximate it to Gaussian functions. And you had three different Gaussian functions to have this to mimic this Slater type orbital. And this is what is referred to as a minimal basis set. So this is called STO3G. So suppose some of you, if you are aware of the keywords, the 3G refers to three Gaussian type orbitals. So you can have one Gaussian orbital, two Gaussian orbital, or three Gaussian orbital. And here if you see, whatever the analytically the Slater type orbital is able to describe, the more closer one is your STO3G. Then comes your 2G and then is a 1G. Right? So this is where I will shift gears and introduce the computational chemistry terms. Enough of quantum chemistry now. Now the computational chemistry kicks in, where you need to now create mathematical functions called basis sets, which can truly reflect the behavior of your system. That's where you have things like, this is from the Gaussian software, which is what my group chiefly uses. So 631G Here star is what? It's a polarization. I'll come to it later. So what it means is now you have a system of electron where you have core electron and you have valence electron. The core electrons are described by 6 Gaussian type functions. The valence electron is again split into 2 groups. One group is described by 3 Gaussian functions and the other group is described by 1 Gaussian function. The star is added for a depolarization. So this is to have the polarization effect. So you can have 1D and you can have a p polarization also. So those are represented by star and star star or d comma p or 2d comma 2p. This 3-1 can further be split into 3-1-1. That is just having this is called a split valence triple zeta basis set, which is it adds 1 Gaussian type orbital to 631G, right? So these are some basic I'm trying to explain to you because at this stage, if you understand the terminology, then it will become easier for you when you handle the software yourself and come across other abbreviations like this. What I have not introduced is Dunning basis set, which is shown below. So here CC means correlation consistent. P V double zeta. So P is polarization, V is a valence orbital, and double zeta. T is triple zeta, Q is quadruple zeta, and phi z is quintuple zeta. So the bottom ones are called Dunning basis set. Dunning is another computational chemist's name who had independently contributed. Ultimately, you remember, we need to mimic the true behavior, which is here red line. This is for one electron system, but for multi-electron system, the true behavior will be something different. So different people have come up with different mathematical propositions. The popular ones used in the Gaussian software are the Pople basis set and the Dunning basis set. That much is what you need to know as an introductory level. So you have at least 24 keywords with basis sets. So in the beginning, you may be confused which one to choose. Basically, you need to answer these questions. What do you want to know? How accurate does the prediction need to be? How much time can be devoted to the problem? What approximations are being made? So one has to keep in mind these 4 questions, and all the answers to these questions will what determine which basis set you will use, which level of theory you will use. Okay? Because if you understand this matrix very clearly, on the horizontal axis from left to right, the electron correlation is improving. What do I mean by electron correlation? See, in the case of hydrogen atom, you have only 1 electron. So there is no correlation coming into picture at all. But if you go to helium atom, it's a 2 electron system. I said that the interelectronic repulsion term makes the system unsolvable. So this needs to have approximate methods. Now, whole chemistry, our chemistry depends upon carbon, hydrogen, oxygen, sulfur, nitrogen. So these are multi-electron systems. You will have lots and lots of correlations coming into picture. So, accommodate all these correlations, different theories are developed. So on the horizontal axis from left to right, the sophistication of the theory increases, right? MP2 is a perturbation theory, HF is a Hartree-Fock theory. So this is perturbation theory of order 2. This is perturbation theory of order 4. This is correlation included single, double, triple, CIS calculations. And this is fully correlation included, full CI calculation, which is called the CBS limit will be reached. On the vertical axis, if you see vertically what the basis set, the size with which, what is the basis set? This is a function on which you are going to apply the operator. So this is nothing but our function. Remember all the background that I had given to you. This is the basic, the function that we are defining. And the function sophistication, the size of the function will increase, is increasing from top to bottom. So depending, remember these 4 questions. Now, depending upon our answer, our infrastructure, we have to decide where we can park. We can park it here. STO3GHF is the beginning, very beginning primitive calculation, and infinite basis set and full CI is the exact solution. So you have a spectra of avenues to choose, and that's how the results also will vary from one calculation to the other calculation. Okay. So with this background in both quantum and computational, the next 10 or 15 minutes, I'll present the results on alkane thiols, which my group has very recently done and published. So I'll basically show the results of 2 molecules, very simple molecules, ethane thiol and propane thiol. So ethane thiol is a very simple molecule, C2H5, C2H6S or CH3CH2SH. Now, from a physical chemistry point of view and from quantum chemistry point of view, we are interested to look at its conformation. So basically, my group does conformation analysis of simple organic molecules. And also at times, if we are successful, if the experiment is successful, through spectroscopic method, we kind of detect the conformation, and with theoretical computational methods, we support those experimentally observed conformation. So if you look at there are 2 conformation angles possible. You can look at it from the CS bond or from the CC bond. The CS bond Newman projection is what is shown in 1. So this is your Newman projection of the CS bond, and this is the Newman projection of your CC bond, and you can expect different conformation arising of these 2 projections. If you review the literature past work, there has been a lot of ambiguity in the literature. Even as latest as 2014, the experimental methods are observed. People have not come out with a clarity from computational point of view as to which conformation is seen in the experiment. So we took this up, and we are happy. I'm happy to share that we are able to give a detailed analysis of the computational controversy in the computational aspect of this ethane thiol molecule. If you look at the CC bond rotation, if you rotate the CC bond by 360 degrees, you get this potential energy surface. This is called a potential energy surface, where on x-axis you have one of the coordinates of the molecule, and y-axis is the energy. In this case, the coordinate that I have chosen is the dihedral angle, which is changing by virtue of rotating the CC bond. And you can see here there are 3 distinct minima and there are corresponding maxima. The interest for us is the minima here, and if you see here, these 2 minima, that is the first minima and the second minima as well as the third minima, are degenerate. All of them not only have a similar energy, but they all share the similar structure as well. So the conformation arising out of rotating this CC dihedral angle is just one conformation. Whereas if you rotate if you change the dihedral angle by rotating this CS bond, if you see there are 2 distinct actually 3 minimas are observed, but from that the first minima and the third minima are exactly the same. I will not say identical, but from NMR point of view, they are the same. Whereas this anti-conformer is slightly of a different conformer. So that's why its energy is also slightly different from the other 2 minima. Right? So whereas in the CC bond, you had just one global minimum, although there are 3 different minima, this can be understood as just one global minimum. In the case of CS bond rotation, although there are 2 global minima, these 2 are identical, so that will be considered as one global minimum, and you have another local minimum here. So in a sense, for this one, and we also did a 2-dimension analysis. So in this previous 2 plots, if you see, it's a contour plot where you change only this one dimension, one parameter, but if I change both the parameters, both the dihedral angles, if I change it simultaneously, I get a surface, and that also confirms the presence of only such conformers as I described to you from the contour plot. So this, then you have prominently your gauche and the anti-conformer, and if you look at this in summary, the CS bond rotation give rise to two conformers of the ethane thiol molecule. One is at anti-form, the other one, two minima, are the gauche form. And these are the only, and this gauche form that you get is a similar conformer that arises out from the CC bond rotation also. So these predictions have very good agreement with the experimental result that has been reported in the literature. And additionally, we also give justification for this gauche conformer, that why it is stable through NBO, population analysis, NBO calculations, and frontier molecular orbital calculations. So the details I've shown here. Those of you interested can read the paper that has been recently published. I forgot to put the reference here. This is not our paper. This is 1968. First experiment that was done. The latest experiment was done in 2014. And our calculations, I forgot to put our publication in this, but you can search for ethane thiol, put my name. The student who worked on it was Manish Kumar Tripathi. So this was, you can read the details of the justification why this particular conformer is stable. You can read from that paper. Last molecule that I wish to present and close my presentation with you is a propane thiol. And here also the story is similar. When you say propane thiol, there are the empirical formula gives rise to two distinct molecular conformers. One is a 1-propane thiol, the other one is a 2-isopropane thiol. And here also the story is similar, that even though experiments were done, the existing theoretical predictions did not match with the experiment. So we took this up as a challenge again, and my student worked on it. And again, we are happy to share that our results, whatever we reported and published, that it matched with the experiment very well, in a very excellent manner. So unlike ethane thiol, since there is an additional CC bond in this case, the complexity of the conformational space increases, and as a result, you have large number of rotations possible, and consequently, the number of conformers also increase. Here you also need to understand the naming, the nomenclature of the conformer. So again, you have the CC bond and the CS bond. So if you look at it from the CC bond, this is the beta C, okay? Alpha C is the carbon on which the sulfur is attached. Then that's your alpha C. So alpha C and S is your CS bond. Beta C and alpha C is the CC bond, is what I'm referring to here. So the Newman projection along the CC bond looks like this, which is designated as trans. The Newman projection along the CS bond is designated here, and this is referred to as the gauche. So if you have a conformer saying TG, you should understand it as trans with respect to CC bond and gauche with respect to CS bond. If the nomenclature of the conformer is GG, you should understand it as gauche with respect to both CC bond as well as CS bond. Likewise, I have given you the all possibility here. So here, there are multiple rotations possible, as I said. From them, if you see here, the structure is similar for this 4 minima here. And in a sense, you get 4 different conformers as minimum in the case of propane thiol. Anti and gauche with respect to this is a 2p molecule, that is isopropane thiol, and due to by the virtue of symmetry present in the isopropane thiol, the number of conformers decreases because of symmetry arguments. So in this case, the complexity of the conformational space reduces to a large extent, so much so that you have only two conformers possible, that is gauche and anti. And this is again justification for why the minimum conformer is the most stable conformer. I won't get into the details. For those of you interested, you can look at our published result. And this is the NCI plot for the optimized geometries done at coupled cluster, single, double, using Dunning's basis set for all the four minimum energy conformers that we obtained. The minimum energy conformers are TG, GG, TT, and GT. This is similarly for the isopropane thiol molecule. We also kind of calibrated the different theory, and we found that the one which matches, we were looking for the one which matches very close to the experiment, and that you can see from here that CCSD, CBS limit is complete basis set limit. That is acting in that is giving a very good, reasonably good match with the experiment. So CCSD, CBS limit, gives a very good match with the experiment for the 1-propane thiol, although for the 2-propane thiol, the values are not very promising. The values are almost half. Now for comparison, earlier calculated results by Choi et al. Is a recent paper by Choi et al. The values did not come close to the experiment. So in summary, for the 2-propane thiol molecule, you have 4 different conformers, and the order in which these 4 conformers increase in the energy are TG, GG, TT, and GT. And the 2 conformers in the case of isopropane thiol are anti and gauche, with anti as the minimum energy conformer. And we found that in the case of the propane thiol, especially 1-propane thiol, both the CC and the CS bond rotations, dihedral angle, change the dihedral angle plays a crucial role in determining which of the conformers is the lowest energy conformer. And because of looking at the molecule in a much more closer way, our results, whatever computation results we got, matched significantly well with the experimentally reported results. As a closing remark, when we would like to choose which method for which molecule, we must keep in mind that certain things. 1 second. Sorry, I hope my screen is visible.
Sir, screen has not yet come on the screen. Our screen.
Is it still not come?
No, sir. Yeah, sir, it is coming now. Okay. So in a sense, the advantage of doing computational chemistry is that it avoids experimental difficulties. It can confirm the experimental results, interpret the experimental results in different ways, and it can also predict new results. So there have been reports in the past where experimentally predicted conformers which were not observed in the experiment, theoretically predicted conformers which were not observed experimentally, were observed when the experiments are performed newly after the calculations. The newly predicted conformers were confirmed by experiment. So at times even theoretical results can be much advanced than the experiment. Of course, it is very safe. Nobody has died of carrying out computational chemistry. Cost, of course, computational cost is also high, but then compared to experimental cost, the investment in the
computational, compared to experimental cost, investment in computational is much lesser, especially for pharmaceutical industry. Otherwise, you'll have to spend a lot of money in animal drug preparation, then animal trials, so on and so forth. So most importantly, visualization aid is very much there for computational chemistry. But as they say in Hindi, iski lathi usi ki bhais. The lathi is at the hands of all the experimental people, because ultimately whatever sophisticated computation you do, it is the experimental value which is what the world believes. That's where somebody famously said that theoretical results are like a lamppost, which is more of a support to a drunkard than for illumination. And there's also a very famous quote which is attributed to, wrongly perhaps attributed to Einstein, saying that a theory is something that nobody believes except the person who made it. An experiment is something which everybody believes except for the person who did it. So with that, these are some of the references which I normally share, which I normally use for my own teaching as well as presentation. Irine Levin, Macquarie Simon, Sakurai. Coherent Energy is a very standard book, more for physics than for chemistry people. Levin is a very standard quantum chemistry book, and I would urge each of you interested in the topic to refer to that. You have other Indian authors like S.N. Datta and A.K. Chandra, also quantum chemistry by them. And of course, the Gaussian software reference manual also is quite informative, very crisp. And there's a book by the Gaussian thing, computational chemistry book, Exploring Chemistry with Electronic Structure Methods. You can also refer to that. So with that, I thank you all for your patient listening. And I'll be happy if you have any question, if I'm able to answer it, I'll be happy to answer it now. Thank you.
Thank you, sir, for delivering us a wonderful talk. I would like to first have the question from the participant side. Please, you can either type the question or you can ask it vocally. I think there were 2-3 questions which somebody has asked in the chat box. Let me quickly see. I think Ashok has asked a question. Ashok, can you hear us? On the basis of what molecule you have made a selection for the kind of a study, why not you didn't perform for a drug? What is the usefulness of the data in the point of drug discovery? And okay, fine. So, sir, his question is like what is the application part of the conformational analysis?
Good. Question is good. Why I did not do this, why I did not do that, they're beyond the interest of my research group. There are different research groups who concentrate on different aspects of quantum chemistry. My basic interest or my training has been in conformation analysis. So I kind of, beyond that, my expertise is limitation. So I restrict myself to do conformation analysis. That's why we did this. Why we selected this molecule? Well, when my student was searching for initial days for a good research problem, we felt that this is a good gap that we could address quickly and also very efficiently. And hence we selected upon Alkane Thiols. And for this talk, I've presented only 2. But for his PhD thesis, he has worked on a couple of other systems. So Alkane Thiol has been the choice because we saw potential opportunity to work there. We could fill the gap. The application part I have not highlighted, and major application is in the pharmaceutical industry. Of course, for the Alkane Thiols, even its pharmaceutical application, I am not very aware. But there are, as I said in the beginning of my answering also, pharmaceutical application is a different field where people do, and then my concentration is not on that direction. Hope that answers your question.
Correct. Perfectly answered. So, sir means to say that his research interest is to mainly go for the conformer analysis. Application part, you being a drug discoverer or a biopharmacist, you can have a look on that. The next question from the participant. Okay. Sir, I have just one or two questions, not many of them. You said that there is a energy difference of close to 0.5 kilocalorie per mole moving from Gauss to the standard or to the eclipse one. So how easy or difficult is to probe them experimentally? Because I have never gone towards that. The energy difference being so mere value.
That's a good question. Room temperature, they both will interconvert very easily. Now, when you go to temperatures which are less than 10 Kelvin, which is normally realized in supersonic jet expansion or matrix, suppose you have matrix experiments, when you have deposit a helium matrix and you capture these molecules in the helium matrix, there is a possibility of both. That is the supersonic jet expansion, and in the matrix cooled experiment, you can expect to have them separated out. Having said that, in the interstellar medium, where the temperatures are close to 0 Kelvin, there also you can expect the major application of, if there's a question from anybody, I was expecting a question saying, what is the application of studying Alkane Thiol? One application is that these are molecules which are found in interstellar medium, diffuse interstellar medium. So astronomers who through their telescopes, they record the spectra. So our data, computational data, can help them to interpret their astrophysical observations. And in such cases, even a difference of 1 kilocalorie per mole or less than 1 kilocalorie per mole also helps them to existence of the different conformers with the energy difference of 1 kcal per mole is possible in diffuse interstellar medium. But definitely no in the case of room temperature. They will all have room because room temperature is KT or NRT, NKT or RT. That interconversion will be anyway possible in the room temperature.
Correct. So that is possible in your lab. Like, do you make all this confirmation analysis experimentally in the lab?
No, right now I was trained in during my PhD in supersonic jet expansion, where we were going to temperatures less than 10 Kelvin, yet in gas phase.
Yeah.
That is something I wish to inform the audience, that it is less than 10 Kelvin, but it is still in gas phase. You should remember that. That's a special technique. Why? Because like Joule-Thomson effect, what happens in Joule-Thomson effect? When the gas expands from a high pressure zone to a low pressure zone through a very tiny orifice, the tiny orifice is so tiny that the diameter of the orifice will be less than the mean free, the collision path of the gas molecule. If you expand it, what happens? Because of Joule-Thomson effect, the temperature goes down on expanding. Yet the gas remains in the, the molecule after expanding remains in the gas phase. So this was observed, called a Joule-Thomson cooling, which is very famous. In supersonic jet expansion, a similar, the same phenomenon is exploited. But what is done is the orifice diameter is slightly increased so that when the gas is expanding, there is a collision happening, and then you have further cooling down. So when the pressure changes by 6 orders of magnitude, from 10 to the power 6 bar to say or say 1 bar to 10 to the power minus 6 bar, or when the pressure changes by 6 orders of magnitude, the temperature drops down to less than 10 Kelvin and yet remains in the gas phase. So that was during my PhD time we did that. In my postdoc time, I was doing the matrix isolation technique, but right now these two I have I'm not pursuing them. Right now I'm doing room temperature spectroscopy only. So experimentally, I will not be in a position to see them in my lab at the moment.
Okay. So that was my query. So with that, if there is any more question, please ask. Otherwise, I'll free the sir because he's having a very busy schedule. Any more question from any one of you? Great. So with that, I'll thank Doctor for giving us a very valuable time and providing us a very informative session. Now, one thing which I very much liked in the session is, now, see, in the training part, we are learning about all these bases and the functional, but what are the applicability of it and what is the meaning of this 6311G, 321G? It was very extremely elaborated by the sir. So nice fitting and approximations accuracy. I hope the bridge, which we were rather lacking in our training and in the theory part, that was very beautifully covered by the sir. So with that, I'll again thank sir from the audience and the participant side as well. I think, sir, we can terminate the session now, and I'll continue with my training part.
Okay.
Thanks.
Thank you very much. Thank you very much, and thanks the audience for their patience. Namaste.
Yeah. Sure. Yeah. Just a second, guys. I'll just stop the recording part.